And then I want. So during that time, like here,
No.
down, whatever you feel. And you want to the weight of her arm. Oh, no, she's. The lights are better line. Just, yeah, you can. Otherwise. Whatever you feel.
That's right.
Oh, no, she's.
I'm working on it.
The lights are better line. Just, yeah, you can. Otherwise. Whatever you feel.
That's right.
Oh, no, she's.
I'm working on it.
The lights are better line. Regardless, just, yeah, you can. Otherwise. Whatever you feel.
That's right.
Oh, no, she's.
I'm working on it.
The lights are better line. Regardless, just, yeah, you can. Otherwise.
I bet they're trying to run it here. As long as it's trying to get education, more power to you. Oh, yeah. Yeah. Oh, yeah. Yeah. And I would take yeah.
You get the job.
Outside. Yeah.
Good talk.
Yeah. Take them outside and be on the rock wall and.
Get each other.
Oh, George.
Oh, yeah, right.
Yeah. Oh, yeah. We're warm guys. Yeah. As I say, you have to afford that and it takes. Yeah. Oh, it was kind of like, yeah, you know, but you're it's a good idea. It's run over.
Yeah.
Look over here. Don't reach one and turn it on. My dad was. Yes. Found it out. Right. I can't see, right?
Welcome, everyone. Good to see everyone. My name is Crystal Hopper Myers, and I am our STEAM Pathways Assistant here at SWOCC. This is your first time on campus. Thank you for coming, and feel free to kind of wander around our Umpqua Hall and check out the different labs and classes that are here. It's a really pretty building, and we're grateful for the community for providing that. Tonight, I'm really excited about our lecture. We have one of our own, Frazier Pruett, here to speak with you today. And so I was really happy when I asked if he'd like to come talk. He said yes. So here in a moment, Dr. Coiner will come up and introduce him. I always like to kind of start out by just telling a little bit about some exciting things that are happening right now. We have a lot of exciting things to talk about, but I'll just kind of pick out a few. The first thing, I'm super proud of our awesome SPEAR team. That's our student research team that's made up of a variety of different students. We have geology, biology, chemistry, physics, engineering. We have all, we even have some students doing research with our psychology professor. So it's pretty neat to see that. This kind of started out with just mostly physics and engineering, and now it's just kind of branched off to various science fields. So I'm really excited to see that happening. They've stayed very busy, especially the end of last year going into this year. We have a big team of student researchers working on a project out at Fossil Point, which is led by Dr. Wynn McLaughlin, who's our geology professor, who's here today if you have any questions. She also, Wynn is working with, we have Dr. Coiner, we have Amy Burgess, our biology professor, Derek Morelli, our chemistry professor. We've just got this really awesome team working together on that project. On top of that, we have some amazing high school students who have actually been participating in our new high school STEM internship program, doing hands-on research, getting to earn money, which is amazing. This is just great opportunity that the Oregon Coast STEM Hub, the Oregon Community Foundation had made possible. I recently joined the Leadership Council for Oregon Coast STEM Hub. They're just an amazing program, and I'm proud to help represent SWOCC with that program. I didn't mention that our Faculty Research Award actually our Fossil Point project was made possible by Oregon NASA Space Grant, Faculty Research Award, and we've also recently had NASA Space Grant they have awarded some of our students the STAR Award to do research. So we're so grateful for all of these amazing organizations making these opportunities possible for our students, which has been huge. So with that said, I could go on forever. We've got lots of events happening, lots of lectures that'll be happening regular in this room. I've got a lot of them scheduled for a Tuesday at 6 p.m. Hopefully that works for you all. And so please be on the lookout for those. We also have various dates that are planned. One at the end of this month where you can come out and visit our portable planetarium at the Coos Bay Fire Department, which is in partnership with the Coos Bay Public Library. So with that said, I'd like to introduce Dr. Aaron Coiner. He's over our physics and engineering department here. He's going to give you a little bit of information about our guest speaker, Dr. Coiner. Thank you.
All right. Thank you, everybody, for coming. Today is a good one of it's a good way to start this term of lectures, and I like the way our lecture series has gone recently, just because we have a wide array of different topics. From the last one we had was the physics of anime. Now we get to look at solar cells. Later on, we'll get to look at sea otters later in the term. So there is a wide array of science that we talk about in this building. I was happy, much like Crystal said, I was also happy that Frazier agreed to come speak. I know there came a time about, what is it now, 3 or 4 years ago, that I think it's 4 years ago, that it became rather imperative that I find other engineers to bring onto the SWOCC campus to help our engineering program grow. And Frazier was one of the first ones to step up to help with that. He's been working with us as the instructor for our electrical fundamentals courses for the last few years, while also being an engineering consultant for a number of different local companies, including Bespoke Power. He has a multi-decade career in the field of electrical engineering, focusing mainly on power systems of various types, everything from working on lighting systems for aircraft to what I think there's about 57 other things that you've mentioned at various times. Yeah. One of the joys of being a practicing engineer is you do get a wide range of experiences, whether you started that way or not. Things do tend to spread out the different activities. But we are extremely grateful to have Frazier come in, and we will learn a lot more about solar PV panels today. And with that, I will hand it off to you.
Very good. Thank you, Ray. Appreciate it. Well, thank you for being here tonight. We're going to be talking about solar energy. Now, solar energy comes in a lot of different forms. One of the most fundamental, of course, would be solar thermal energy. And we get our daily dose of solar thermal energy every day from the sun. And in fact, if it weren't for that, it would make life very difficult on this planet, if not outright impossible. So, but today we're going to be talking about direct conversion of solar energy into electricity. Just so you know, I like interaction, but let's keep the questions till the end. There'll be a chance for you to ask your questions at the end if you are still here at the end and care. So we will try to answer your question. This is one part of a 3-part series. So if I gave you the entire series tonight, you would probably lose you after a couple of hours. So we'll try to keep this to about an hour-ish, and also leave some time for Q&A. Then today, the first part is going to be talking about solar, the small individual cells. And the next part is going to be talking about solar panels. That's where we take all these cells and we integrate them into a panel that gets installed on your roof or someplace. And the last part, we're going to be talking about solar arrays. So when we take these panels and we connect them together to get more power, we have a solar array. And that would be something like might be installed on your roof. Also, the utilities have solar panels, and they create power from that and send that out to the grid. Okay. As Dr. Pointer said, I have been doing this for a very long time. I have worked in a startup company in Tualatin, and there were a group of PhDs from Oregon State University that started the company called Azure Technology. And the idea was to create power conversion technology that would facilitate maximizing energy harvest. So that's what it's all about, is getting the most out of our solar cells. Oh, get the right one. What am I doing wrong? Just do this. There we go.
Now that it's back on the now it should work.
Okay. Very good. You'd think somebody that works in a technology field would be a little more comfortable with it. As a matter of fact, I'm not a big fan of technology. So when we talk about, we're going to use terms, and I want to define these terms so that when they come up, you get an idea of what we're talking about. The first one is PV, which is kind of short for photovoltaic. That is that we turn photons into volts and amps that we can directly use for other things. Solar energy. Now, solar energy is a very broad term. It can be photovoltaics. It can also be solar thermal. It could be, in terms of making power, have you ever heard of the Tower of Power? That was another way of turning solar energy into electricity by using mirrors to focus the sun on a boiler that created steam that turned a generator that made electricity. Thermal solar is something we use for years ago. There was a big emphasis on thermal solar for like solar hot water heaters for your house. It would fit up on top of your house. It would heat your water, and it would do that with a relatively small panel. That's thermal solar. And these are all forms of solar energy. Now, here's one that might throw you. Insulation. Now, this is not the stuff that goes in the walls of your house. Okay, that's insulation. This is insolation, which is a measure of the radiant energy of the sun. So insolation is what we're trying to gather, what we're trying to harvest. Grid-tied inverters. So in order to get the power from the solar cells into a form that's usable for the grid, we have to convert the DC voltage from the cells into an AC voltage that is compatible with our grid. So to do that, we have something called a grid-tied inverter. And we'll be talking about that more when we get to the third installation of this. Islanding. Okay, that has nothing to do with living on an island, I'll tell you. But when we talk about distributed energy, which is what solar energy is. So in our system, the way it's designed right now, we have power plants that are remotely located and they generate lots of power. So, and we know recently, sometimes that power goes out, and that power can go out because of wind. Usually some kind of a weather event causes them to go out, or perhaps an accident. So when you have distributed generation, let's say at your house, the linemen that come out to work on the power lines, they know that if your house is downstream from where they're working, there's no live power there and they're safe. If we didn't have anti-islanding, your solar installation would keep producing power and pushing it back up the line, and it's hazardous for the people who are working on the power grid. So that's why we have this thing called anti-islanding, and it's a legal requirement. You cannot just keep pumping power into the grid if the grid goes away. And we'll talk about how do you know if there's a grid present or not. Okay. MPPT, maximum power point tracking. Now, as we get into the information I'm going to present tonight, you're going to see that solar cells produce the most power at a particular point. So we want to find out what that point is, and we want to stay there because we want to get the most energy that we can possibly get out of our solar array. One, because they're rather expensive, and we've been promised that at some point it'll pay itself back. So we need to get the most power that we can possibly get out of that. Okay, insolation is a measure of solar energy. Now, in ideal conditions, we receive about 1 kilowatt per square meter. That's rather a lot. So the average house can live on anywhere between 3 and 5 kilowatts of power. So you could say, well, I only need, 3 to 5 square meters, which really isn't all that much, until you realize that solar panels aren't all that efficient. So then you're going to need a lot more of them. So 1 kilowatt per square meter, and a lot of that energy can be turned into electric power. It can also be turned into heat. There are some designs that do both. In fact, that's one of the approaches, is to use the back of the solar panel to gather thermal energy from the sun while you're getting electric power from the panel. And there's some advantages of that. Now, you might be thinking, maybe in water electricity mixing is not such a good thing. I can tell you, I don't know of any systems that are actively functioning that way, but it is something that we look at because temperature is an important parameter when we talk about solar energy. Distributed generation. That means that power is generated in remote sites. It could be a large utility scale site, or it could be your house. Recently, there's the wind power has been in the news around here. There was an investigation of putting wind turbines out in the ocean to gather energy, and that is another form of distributed generation. And one of the things about distributed generation is not all of them are owned by the power company. In other words, the power from your house is owned by your array, what you put out there. So the power company doesn't necessarily get to control that. Okay. Now, distributed generation is not a particularly new concept. It goes back to Thomas Edison. So if you remember, Thomas Edison, his system, he liked DC. He was a DC guy. Now, the problem with DC is it doesn't transform very well, which means he needed to have a power substation every few blocks to give everybody enough power. Because he wasn't stepping the voltage up, he had very high currents to deal with. And there were a lot of losses in the distribution system for that. Then comes along Tesla. Tesla had a better idea. And he used the idea of AC to transform voltage from the generators to a very high voltage that could be transmitted efficiently over long distances, which is the system that we use today. But distributed generation has taken on some new meaning as we begin to add solar installations or wind installations. Perhaps you've been out to Eastern Oregon and seen a lot of the wind generators out there. And they tend to put them in places where wind blows. Part of the problem with distributed generation is it's not particularly reliable. So if you have a coal burning plant or a dam on the Columbia River, you get a good idea of how much power you're going to get out. It's pretty reliable. Power companies understand what it takes to create that kind of power. And they have different levels of power. Okay, the cheapest power is the one that runs all the time. And then as load increases, they bring on different kinds of generation to handle the load. But the power companies don't own distributed generation that's on your property. If you have a solar, let's say your solar array goes down, well, it just goes down and they have to deal with it. So this actually presents a fairly significant challenge to the power companies of how they're to regulate power coming into your house. By law, the power company is obligated to give you power that is within plus or minus 5% of the nominal mains. Now you go, well, plus or minus 5%, that's a lot. Well, I'll tell you, compared to what the rest of the world deals with, that's excellent. Europe is 10%. Places like Australia are 10%. Japan, 15% on a good day. So the quality of power that we have in the United States is second to none. Now, our infrastructure is starting to be taxed more and more as we bring on things like EVs, which are big electrical loads. And when we don't add new power plants, we have to figure ways to creatively manage how we're going to have electrical energy. Okay. This is what I really wanted to talk about. PV cell characteristics and modeling. So there are different kinds of technologies used for the cells. Monocrystalline, those are cells that are made of a purified silicon ingot. So around the Portland area, there are several companies there that make silicon ingots, Wacker Siltronics and SEH America. And they make these large ingots of silicon, and they're grown from a crystal. And so all the crystals are aligned. And when they have that ingot, they take it and they slice it into wafers. And that's used to make semiconductors of all types. That's kind of the basic building block. Polycrystalline, it's a little bit different. The crystals are not necessarily aligned. You will notice a polycrystalline panel. Usually they're blue, and when you look at them, you'll see a different grain structure in the cell. They're cheaper to make. That's one of the things about that. And then we have amorphous silicon. So that means it's somewhat randomized. Again, these are different technologies. There are only a few that are really popular, and we're going to talk about the trade-offs of those. Then there's thin film. Thin film has a film that generates voltage, but it generates very high voltage at very low current. Thin film is relatively cheap. These actually are a film. They're bendable. They can be conformed to a surface. You tend to see these in low-cost solar installations. So if you were to go up online and look for them, sometimes they don't have a thick backing to them. They're just cardboard or something like that. So with monocrystalline or polycrystalline or amorphous, these are actually cells that need a significant structure to support them. Otherwise, they'll break. And that's a problem. Now, one of the interesting things about solar cells is they are current sources. So now this is where we kind of get into the more technical parts of this. So in electrical terms, we generally get power from two sources. It's either a current source or a voltage source. Most sources that we use, including your wall outlets, these are all voltage sources. Most batteries are voltage sources. Solar cells are just about the only naturally occurring current sources. So let me frame this up a little. With a voltage source, the terminal voltage is fixed regardless of the load. So whether current's going in or out, the voltage is fixed. A current source generates a fixed current, more or less regardless of the terminal voltage of the device. And they each have their particular uses. But by and large, most sources that we will run into are voltage sources. Now, what else are current sources used for? Perhaps you've ever done some welding or knew someone that did some welding. Well, welders are current sources. Now, they're man-made current sources. They're not naturally occurring. But in order to make that arc stable, you have to control the current. So that's one of the settings you'll have on a welder, is the current setting. Now, that's important because solar panels can inadvertently turn into welders. And that's bad because welders generate heat, a lot of heat, and that generates a lot of fire. So fires on solar arrays is a real concern. You can get arcing in the contacts. Recently, the National Electric Code has been updated to include arc fault detection in bedrooms. It's now code to have arc fault detection in bedrooms. We've had ground fault detectors for a long, long time, but arc fault detectors are there to prevent something catching fire because of an arc in the electric system. Okay, and this is the same kind of problem that you're going to have in a solar array. One thing you don't want to do in a solar array is unplug it while it's operating. That's bad. And after they come and get your body, we will tell other people not to do that. Okay. Solar cells are built based on a large PN junction silicon device called a diode. Now, these cells range in size. It depends on the manufacturer. Our wafer technology is now up to about 12 inches in diameter, although mostly we're talking about wafers that are in the 6 to 8 inch range. And they're arranged on the panel. And these are all diodes. Now, one good thing about these diodes is they don't have to be particularly good diodes. So we can tolerate a fair amount of contaminants. Perhaps you've seen a place where they make semiconductors and they're in their little bunny suits there, and they're in a class 1000 or a class 100 or a class 10 clean room. And that is parts per million of contaminants inside there. And contaminants are one of the #1 killers of semiconductors. It'll reduce yields. Now, as it turns out, solar panels can have pretty ugly contamination and still work. That's a good thing, which means they can be done relatively cheaply compared to, say, a new processor. Okay? And because it has a single junction, there's a positive side and a negative side, and we're going to talk about what diodes do. We don't typically use them as a solar cell. They have other functions in electrical engineering. Okay. The cell voltage is in the 0.6 to 0.7 volt range. So if you took a single cell and you illuminated it and you measured the voltage, you'd get 0.6 to 0.7 volts. Not a lot, really. So how do we fix that? Well, we have to put them in series And this is kind of a model. This is a typical model for a single cell. Now, the thing called IPH is a current source that is a current that is proportional to the incident radiation. Now, the little thing there that's a triangle with a line, that's the symbol for a diode. And the negative side of the diode is the line. And the top end is the positive side. We call that the anode, and the negative side we call the cathode. So you can see that that diode is across the current source. So when there's no load, the current from that current source goes through the internal diode of the cell, and it kind of gets consumed as heat. The resistors, the RSH and the RS, these are parasitic resistances that exist in the cell. We don't add them in there. They exist naturally. They represent losses in energy. So we always want to optimize what those are. So back in the 1940s, AT&T Bell Lab was looking at solid state physics, and they got to looking at semiconductors. And Dr. William Shockley, whose namesake for the Shockley equation, worked for AT&T Bell Labs. And in the process of working on solid state semiconductor materials, by the way, there are many of them. There's not just one, okay? There's probably a handful, and we keep developing new ones to overcome some of the problems with the old ones. And they do tend to get better, whether we're trying to make something that's going faster or is lower on resistance, lower losses. And these developments come rather slowly. So today we talk about materials like gallium nitride and silicon carbide. These are the new kids on the block, and they've actually been around in the industry for about 5 years. Prior to that, we had silicon, which is still the mainstay of the semiconductor market. The good thing about silicon is that it is the second most abundant element on Earth. So we're not going to run out of it anytime soon. The others have to be man-made. So Dr. Shockley derived this equation to describe the behavior of the diode when you look at its current and its voltage. So some of the terms used here, I of S is the reverse saturation current. And that's the current that flows through the diode when a negative bias is put on the diode. The ideality factor, okay, is a SWOCC. It was a number they had to put in there to make the equation kind of work right. Okay, but it's a number that is either 1 or 2 generally. And VT, we call that the thermal voltage. Now, it's represented by KT over Q, where K is Boltzmann's constant, T is the temperature in Kelvin, and Q is the charge of a single electron. And when you multiply all those together, you get something that is voltage. Now, that voltage is actually rather small. In fact, for room temperature would be approximately 300 Kelvin. That number is 26 millivolts, very small number. And it does change linearly with temperature because of that equation, but we're going to find out that things are not necessarily as they seem. Because if this equation were the, let's say, the absolute equation, we would see that the thermal voltage goes up with temperature. In fact, it goes down with temperature. And let's talk about the thermal effects on the cell itself. So we can either increase or decrease the temperature. Now, solar panels live in a rather hostile environment. They live outside. So if you're in Arizona and you put your solar panels out there, in fact, the upper bound of operating temperature for a typical solar panel could be as high as 90 degrees C. That's close to boiling. It's very hot. Okay, so while Arizona has a lot of sun, they also have a lot of heat. So this is very difficult, and this temperature cycles. Okay, every day the sun comes up and the sun goes down. So the temperature of these panels begin to cycle, and it turns out that thermal cycling is one of the mechanisms that kind of is really tough on electronics. Okay, things start to move, and as they move, they begin to fatigue. So a typical solar panel has a warranty that goes from 20 to 25 years with a guaranteed output. So that's very hard to get something to last that long. So as temperature is increasing, the ISC, by the way, that stands for short circuit current. The short circuit current increases slightly with temperature, and it decreases slightly as the temperature goes down. However, VOC stands for open circuit voltage. That changes quite a bit with temperature. In fact, as the temperature goes up, the open circuit voltage is decreasing. And as the temperature goes down, the open circuit voltage is increasing. So in the United States, the maximum legal open circuit voltage that you can have is 1,000 volts. That is with cold panels. In Europe, it's 1,500 volts. There, give you a little bit more there. Now, the voltage of the cells themselves change quite a bit, depending on the conditions. So open circuit voltage is maximized at the coldest temperature. So what's the coldest temperature we're going to see in around here? If you got down to minus 40 C, that's pretty cold. Okay, you might see that in the continental US. For aerospace applications, the number is minus 55 degrees C. That's even colder. You're definitely going to want a jacket in that. So for the high temperature side, we see temperatures go up to 100 C, 90 C. The panels have to be tested to either 85 or 90, depending on which panel standard they're using. Either way, it's very hot. So when I was at Azure, one of the things we worked on was to put a maximum power point converter on the back of the solar panel. And in order to do that, we did that so that each panel would put out its maximum power kind of independently of what the others were doing. And that meant that all of our electronics had to last at 90 degrees C, and it had to do that for 20 years. None of the panel manufacturers really bought that. So as it turns out, it was a bad marketing idea, okay? But we actually accomplished that. We got it to work. And the company ran out of money before we could do anything else. However, we did learn a lot in the process of doing it. So temperature is a big deal. In fact, Arizona gets more sun than we do, but guess what? We're a lot cooler than Arizona. And you know what? The output of an array in Phoenix and the output of an array here in Oregon, about the same. What we lose in heat, what they gain in sun, we pick up because we're so much cooler operation than they are. And maximum power, as you can see, since it mostly follows the open circuit voltage, is going down as the temperature goes up. Okay, So let's talk about the temperature coefficient. So why is the temperature coefficient negative? If we were to look at the Shockley equation, you would see it looks to be linear in T going up. However, is the Shockley equation wrong? It's not wrong, but it is incomplete. And the big thing that makes it incomplete is the reverse saturation current is a strong function of temperature. And that more than offsets the fact that T is going up for thermal voltage, which is why we end up with a temperature coefficient of -2 millivolts per degree C for a typical junction diode. Now, when I gave you the numbers about the voltage for a particular cell, that was based on a silicon cell. If cells are made out of different material, they're going to have different voltages. So the voltage goes down. So if something is 100 degrees, there's a 100-degree swing, it's going to drop about 200 millivolts per cell. When you look at that as a percentage of 0.7 volts, that's a big percentage. So the effects of temperature can't be understated. Now I gave you these terms. Should have done that first. Short circuit current. So now, remember I said if you have a solar array that's operating, you don't want to unplug it right away. As it turns out, the most safe way to handle solar panels is by shorting them out. Now that's kind of counterintuitive, but because they're current sources and you short them out, you don't have a lot of power because there's not a lot of power in a short circuit. Now you couldn't do this with a voltage source. You'd have lots of current there and you'd have lots of arcing and other bad things going on. But because this is a current source, it has a limited current and you can short that panel out, and that is one of the safest ways to handle it. Open circuit voltage. Now, let's just say in an idealized current source, the open circuit voltage is not inherently limited. It has to be limited by the load that's placed on it. But let me back up a couple slides here. But you can see in this model, the diode that's across the current source is the voltage limiting factor for the panel. If that diode was not there, in principle, the voltage could be much, much higher. But the diode structure is actually part of the cell. It's not something we can just arbitrarily get rid of. It's going to be there. Okay, so I ran some simulations on cells. This is a single cell, by the way. And just so you know, as an engineer, when I'm talking to students, I often use terms that I'm very familiar with and a VI curve. And I realized that hadn't really fully explained things when they wanted to know, what is a 6 curve? Well, it's not a 6, it's a voltage and current curve. So I have to be careful that I explain new things to my students so they understand and they don't start going, well, I have no idea what a 6 curve is. I couldn't find anything on that. So this is a voltage on the vertical axis versus current on the horizontal axis. Now these numbers are fairly typical. 8 amps is not unusual for a solar panel to be able to put out, which is quite a lot, but keep in mind there's a lot of area in the cell. It can be higher. I have seen some that were in the neighborhood of 12 amps. You don't really see many that big. Again, it is kind of a function of how big the cell is. So the bigger the cell is, the more short circuit current you're going to get. Now the voltage is really not dependent upon the size of the cell. It is dependent upon what the cell is made of. So most of these cells we're talking about are made of silicon. So having an open circuit voltage in the neighborhood of 700 millivolts is fairly typical for silicon. And silicon has been our go-to material for over 60 years. Okay, if you played with electronics in the early day, you probably ran into selenium diodes and germanium diodes, which are pretty much obsolete now. Nobody makes them anymore. But those were some of the first semiconductor materials. Now, what's interesting about this curve is you'll know that the voltage stays not exactly constant, but it stays high until it gets to a point. Can you see that? Okay. You get to something that's the knee of the curve, and suddenly the voltage starts dropping quite rapidly as you approach the short circuit current of the cell. And toward the bottom here, the curve is almost completely vertical. So when it gets to whatever the maximum current that it can put out, that's all you're going to get. Now, this is a little bit more interesting curve. So this is power versus short circuit current. So power, and this is again for a single cell, power is on the vertical axis, current is on the horizontal axis. Now this one is a little bit more interesting. You'll notice that the power kind of increases more or less linearly until you reach the top, and then it drops off rather suddenly. Okay. This is an interesting curve because the top of the curve is the maximum power that you can extract from that particular cell. And that's where we want to live. We want to live where we're taking the most power out of the cell. Now, this is from a controls point of view, it's a little bit challenging. And I say that because, oops, go back. I say that because once you hit the top, if you go too far, you're going to drop off rather suddenly. And if you go back, you're going to be losing power. So we're going to talk about methods that we stay at the top of the curve. We want to live there. So we have to keep hunting. Now, having said that, the shape of this curve changes through the day, depending on incident radiation, depending on contamination on the panel, depending on shading. And in fact, you can end up with two relative maximums on this particular curve. Now, sometimes the algorithm for finding the maximum power point can get fooled and it'll get stuck at the wrong relative maximum. So sometimes in the process of looking for the relative maximum, they have to do a sweep of the panel. In other words, they will turn the converter completely off and start from zero and go all the way to maximum current. And then it'll look for a new the absolute maximum. Now, this is my SPICE model. If you're not familiar with SPICE, it's a very old public domain program used for simulating semiconductors. It's often called Berkeley SPICE. And it allows us to model electric circuits, but it's more powerful than just that. It gives us the ability to create mathematical models and install them in our circuit. So we don't just have to make circuits out of components and hook them up, which is one way we use it, but we can also, there it is. We can make definitions using an arbitrary behavioral model. These are very, very handy. And they allow us to create any function we want just as a mathematical model. And it simplifies it. And this is based upon an extension of the Shockley equation. So you can see up here is some of the input. Okay, these are parameter statements that we use to pass parameters into the model, and it allows us to change the parameters. Now, we can change the parameters by actually typing them in, but sometimes it's more convenient to use a param statement. And if you're interested in having a copy of SPICE, a company called Analog Devices. In fact, this is the one we recommend to our students. It's called LT SPICE. And that's exactly what this is. There are many companies that make it because SPICE is a public domain program. They can't charge for it, but they will charge you for the shell that's around it that allows you to draw schematics. Now, is LT SPICE the best simulator out there? No, but it is the cheapest because it's free. So free is a very good price, and I use it a lot. So if you're interested to play around with electric circuits as a hobbyist or as an engineer, this is the way to go. Okay, so this is a model of a multi-cell array. Now I can put in things other than one cell's worth. You see here, the open circuit voltage is 233. That was based on a simulation I was doing for a client in Canada. They wanted me to make a solar panel tester. So, and these are the parameters they gave me. They said it has to operate between this voltage and this voltage and this current and this current. And they want to do a sweep on the panel. So I was able to simulate how the panel simulator would work. But you can see it's a relatively simple model. And we can change both the short circuit current and the open circuit voltage to simulate more or less panels. Okay, now as we get into a multi-cell array, you'll notice that the voltage is much, much higher than it was with the single. It's now in the neighborhood of 233 volts. But you notice the current is really not changed. The reason the voltage is higher is because the way we connect the cells into an array is we connect them in series. Now, having said that, this is the first thing I tell my students. This is not how you hook up current sources. You do not hook them in series. However, because the voltage is so low, it's very inefficient to try to convert a voltage source that's 0.7 volts. We really can't do it efficiently. So we bite the bullet and we put cells in a series configuration. And there's a lot of problems with that, particularly with current sources. Okay, we get the same looking waveform, but now we're talking about some real power here. We've got something in excess of 1 kilowatt. And you can notice that if you get off the maximum power point, you could lose quite a bit, particularly if you keep going that direction. It drops off rather rapidly. It's much softer climbing the hill. Once you get to the top, it drops off very rapidly. So this becomes a constant monitoring of the panel by the inverter. It has to look at the voltage and keep looking for the maximum power point. Okay, in terms of the operating modes of the cells, we have 3 operating modes: normal, no load, and driven. So in normal mode, the red arrow shows you that the current is going out the cell and it's producing power. That's what we want to be happening. Now, the current source is completely dependent upon the incident radiation on the cell. So presumably all of these panels are in the same environment and are all seeing the same incident radiation. But that can be different if you have some shading on the panel, and shading could come in the form of a tree or a pole or leaves or dirt. Okay, all of these things cause problems. In fact, in the desert, you think, well, there's no trees out there, there's no leaves, there's no poles, there's nothing out there. But what they have a lot of is sand. and sand blows. And what happens when sand blows, it sandblasts the panels. And once the panel's surface gets sandblasted, they don't pass as much light as they used to. So sand can also lay on the panels, it can accumulate on them. So it can also block light from getting in. So there's no perfect environment. You're always going to have to deal with something that could be hurting your solar output. Now, you may have to have regular, somebody go out there regularly and clean the panels off. That's true. If it's up on your roof, that might be you climbing up on the roof, trying to get the leaves off your roof. Perhaps not a very safe place to be. Okay, so this is normal mode. Our current source is putting current out. Okay, no load. No load means there is nothing connected to the output of the cell. Now the current that's generated by the cell has to go somewhere. So it gets consumed by its own internal diode. Now what that does is that kind of converts into heat. Now the good thing is, as you saw, the amount of power in any single cell is probably no more than a few watts. So given that a cell is about this big, they don't really get all that hot. So this power does turn into heat, but it's so distributed, it doesn't do any damage to the cell. That's okay. Now this one is one we want to avoid. Okay, this is driven. So there could be cases where the current in blue is coming from the outside and it's being driven into the cell. And it will go through the internal diode of the cell. But you notice that the current is not going in the direction you want it to go. Okay, you want to be producing current. You don't want to be absorbing current. But what can happen if you have two cells connected in parallel, if they're not illuminated the same, they won't share. And one could be backdriving another. And this is a real problem in arrays. You want to get power out of your array. You don't want part of your array backfeeding another part of your array. Okay? You paid a lot of money for a heater. So you want to get that power out, turn it into AC, and get some money for it. So now, is there actually a valid use for backdriving a panel? And there is. And this is one thing we developed at Azarray because we want to test our products. And what we figured out was that we needed a solar panel simulator. So what simulates a solar panel better than a solar panel? So what we found out is that if we took a power supply and drove current into the panel and hooked our panel up to one of our devices, we would have a pretty good solar simulator. Because when you're trying to test a product, you always want to be able to control the test conditions. And we know how predictable the weather is in Oregon. So when it's sunny, we want it to be sunny, or we want it to be warmer, or we want something that it's not. So in order to test a product, you have to be able to set it up and have a stable test environment. So this is one of the uses of a solar panel. Now, there are other ways to do this. Well, we found out this was one of the cheapest ways to do it because we could get solar panels fairly low cost. Okay, we are now to the second part, which means it's Q&A time. Okay, since most of you have hung in here with me, I now open the floor up for your questions. And Crystal has a microphone so we can hear it. And so it's recorded, and in case we need to.
Yeah. Thank you. Yes, and if you would just raise your hand for your questions. We also have some online viewers and a watch party at our Curry campus. One second.
Say a lynch mob at the Curry campus?
On the new developed telescope that's called the Webb telescope,
Huh?
do they have any continuing processes of solar energy developed for that type of telescope?
I'm not familiar with the Webb telescope. Is this one that's in space?
Yeah.
Yeah, so. Yeah, we really don't have a way to upgrade it. Now, the good news is, there's no weather in space. So as long as it's pointed at the sun, it's pretty much gonna get, good solar. Okay, we're not gonna have anything reduced because of the atmosphere. And we're gonna talk about, effects of the atmosphere. And you know that we have seasons, and you know that the earth is tilted. And Dr. Cornier can talk about this much better than I can. But we know that as we go through, the angle of declination changes. And that means that your solar panel may be pointed in a slightly different direction. Now, you don't have any of that stuff in space, thankfully. So they have the ability to keep it always pointed in one direction. So I don't know for certain, but my guess is, because they have no way to send a repair truck up there, they probably have redundant systems or more capacity than they generally need. One of the things that we don't really do a lot of right now is store energy. So right now, when your array is plugged in, you're delivering energy in real time to the grid. So, what's that? No, okay. So you're delivering energy in real time to the grid. So whatever you're receiving, you're sending it back out. Now, it would be helpful if instead of sending that power out, maybe you had some place to store that energy so that at midnight, when you want to fumble around your house and want to see where you're going, you'd like the lights to come on. So right now, we're just starting to grapple with the energy storage part of that. So, and a lot of that has to do with batteries, of course. So, very good. Thank you. Any other questions?
Question, but then a question out of this, but I'll also follow up a little bit with the Webb telescope. It does have solar panels on it to help power some of the systems. It does have there's a little bit of also some storage. There is some battery storage in it, so it's able to recoup some of the solar energy into batteries to keep it going. There is weather in space. It's just usually in the form of charged particles that try to blow stuff up.
Okay.
But because we can have short circuit flips with a lot of high energy electrons that go through things, and that's what turns satellites into space junk in about 3.4 seconds.
Yes.
But question from this, I know when I was working on things in undergrad and then in grad school, I had a couple of friends that were working on developing sort of semiconductor solar cells to try to get to more efficient ways of converting some of the solar cells. Now the numbers are kind of ridiculous. I think at that time, typical numbers were around 20%. I know I've seen better ones come out, but I don't know what kind of numbers that you've seen recently, and what kind of, have you looked into anything about how that technology is going in terms of improving the efficiency of how these things work?
So right now, we have inverters. Now, an inverter is a device that turns DC, and so our best inverters now have an efficiency in the high 90s. 98 is not unusual. So 20%, that's pretty horrendous, actually. So, but we can't, and this is because we can stack the cells up and get a higher voltage. If we try to do this from a single cell, which would actually be the best way to do it because we don't have any interaction with other cells. But converting power from 0.7 volts to anything else with any kind of decent efficiency right now, not really happening. So now we're going to talk about different inverter technologies. And one of the kind you're going to hear about is called microinverters. Now they're micro in the sense that they're not multiple kilowatts, but they would put out a few hundred watts. And a microinverter is connected to a single panel instead of an array. So that has a host of possibilities. One is you don't need an entire array to put out electric power. You can have one panel. But it also means that you have the efficiency. You don't have a lot of panels interacting. So that's kind of half a step to what Dr. Coyner was talking about. We looked at microinverters, and microinverters aren't quite as good as string inverters. Oops, I'm in the wrong place. But they are still in the mid to high 90s on efficiency. So.
We have an online question from Ashara Clapper. Won't power companies buy energy?
They will. In fact, they're obligated to buy your power. They're not particularly obligated to pay a particular price for your power. So there are multiple ways to monetize solar power. One of them is called net metering, and that is that you produce power and they deliver you power and you pay the difference. That's falling out of style right now. The other is called feed-in tariffs, where you basically sell all your power and then you buy all your power. Now that may sound like, well, that's kind of silly right there. Why don't you just use it? Well, it turns out it's more lucrative to do it that way. Power companies get money for their feed-in tariffs. And there was a time, I'm going back 2010, where feed-in tariffs were in the neighborhood of 50 cents per kilowatt hour. That's a lot. Now they don't pay that over the life of the system, okay, but it allows you to recoup a lot of money early on. So part of the, these systems are designed to last 20 to 25 years. So return on investment varies depending on what you paid up front. Costs have been coming down, but a typical return on investment is 7 to 8 years before it's paid for itself. And then after that, you're into the golden money. Now, after 20 to 25 years, does that mean your system totally goes out? Not necessarily. But we do know that the output drops with. So
I have a question for you, and then we have one more. So I know that we want to do an additional lecture on this in the future. Are you going to be going over this section here for this evening? Okay. And then we haven't announced the date yet, but for I think you have a part 3 as well that you're wanting to put out. So we'll announce that soon for when that is. It'll be probably this fall for that. So
a lot of these are the teasers here, right? Okay. I gave it a really lame name, you wouldn't have showed up tonight. Was a little bit of a provocative name, but hey, it creates interest, right? Hey, as in engineering, we say it's not lying, it's marketing. Okay.
So on those figures with the colored curves, I wasn't paying quite close enough attention and I missed, what is the difference? Each color is different in some way. Was that the ideality factor? What?
No. This was a series of curves that I made where I did I stepped the short circuit current for each curve to get a different curve. So you could see what a family of curves would look like. So
in the real world, how do you change the current exactly?
You don't. It's completely dependent on the incident radiation.
Sorry, how do you change the Oh, so each of these different colored lines represents a different amount of incident radiation?
Yes, this is what would happen if I was looking at different amounts of radiation
Okay, okay.
for the panel, the performance that you would get.
I had that totally backwards. Thank you. Thank you.
Yeah, sorry, that wasn't very clear. Again, engineer brain, I used to talking to a lot of engineers, so sometimes I don't fill in the gaps as well as I should.
Okay, I'm gonna go ahead and take a couple more questions and then I'll let you kind of
Okay.
continue on, okay?
My background is classical thermodynamics,
Okay,
and a lot of the stuff you're talking about is classical thermodynamics, like the Shockley equation.
Yep.
But isn't photovoltaics quantum mechanics, and the gap energies to generate the voltages and the currents is based on the electron energy between the gaps, which is not dependent on temperature? How does temperature come into quantum mechanics?
I'm going to punt on that one. That's not my area of study. I apologize. Stump the speaker night. All right. What's happening?
Well, it's a classical system built around a quantum phenomenon, so you could imagine, there would be a classical dependence on temperature
Right.
from something in there.
No.
But I was gonna say, didn't you talk about a weakness of distributed generation? That's the opposite direction I would expect. I would expect if everybody is able to generate power, then like if one section of the grid gets cut off, then it has an independence because it's able to generate its own resource.
Well, if you're talking that if one part goes down, another part could potentially pick up the load for that. So the problem right now is the amount we depend on, let's say solar or wind, is a relatively small percentage. It's something in the single digits. The power companies really don't like distributed generation because they depend on unreliable inputs like wind speed and solar. If it rains one day, you're not going to get as much out. So they're looking for things that are a little bit more predictable. So that's the weakness from the power company's point of view. So one of the things that's interesting is if you ever go out to Eastern Oregon, you'll find a whole lot of those wind turbines aren't spinning, and they can furlough those at will. So yeah, that's not necessarily giving us all the power that's available. So they like power that's very predictable. Coal's very predictable. Nuclear is very predictable. Dams are pretty predictable. They understand the load side of the curves really well. So if you were to get data from the power company, you would know they know when people are getting up and when they're going to work and when they're coming home and when they're doing things. What they lack with distributed generation is a good view of what's happening on the supply side. So, and if you run out of power, well, then you end up with rolling blackouts and things like that. So, but again, relative to the world, we have pretty good infrastructure. Okay, but have you noticed any new power plants going in recently? Not really happening. So we want to, dams are pretty good. They're original green power. But if we really want to, nuclear is going to get to be more popular. It's going to have to, right? If we're going to.
I would think pumped hydro. You could just increase the potential of water that's distributed via another grid. And then you've got multiple resources to supply water and air pressure. But you have a big environmental pushback on hydro.
Yeah.
Because you're killing fish.
Yeah, that's
taking away fishing grounds for indigenous people. So we're pulling out dams, pulling out hydro.
so.
Pumped hydro could be a lot of fishes. California's put a new grid for 5% pumped hydro.
So, yeah, this is a problem, particularly as we start to bring on things like electric vehicles, right? Did anybody think that these things take a lot of power? take a lot of peak power to charge them up. So
I wanted to know at that point as well, you mentioned that they're a load, but they're also sources.
they can be, but they have to be set up to be that way. So it,
Isn't it a symmetric system? Isn't the grid symmetric so that if they can be load, then as they're plugged in at night, if we want to pull away from a 50% charged battery, we can potentially, given like a software.
that's not obviously true in with the chargers. Most of them are unidirectional. So
About since we got current people online, go to part 2 and we can take up questions after.
well, we're about to the end of our time. We're going about an hour and 15 minutes. I told you we try to keep it to that.
Then the people out in the world need to be hearing about it.
Yeah.
That's a good break point.
Pull that up
Okay.
real quick. Up there.
We have any other?
We have from Derek Morelli, which is our chemistry professor here, Is there an optimal temperature for solar panels where any colder and the efficiency is lost? And then also he went on to say, or is it just that the colder the panel is, the more efficient it is?
Generally, there's no place where it goes negative again, at least in any reasonable place you'd want to live. So, and keep in mind, it's pretty cool space. So,
Does anyone in here have some more questions? Over here, okay.
very good. One more?
So in your opinion, is solar energy a good thing or is it snake oil?
I knew somebody was going to ask that. So the answer is it's a little of both. So there's no hard and fast answer. So does solar energy work? Yes, it works. Does it produce power? Yes, it produces power. Is it going to replace everything we've got? No, it's not. So in terms of energy density, it's on the low side. So in terms of how much power it produces for the size of the installation, it's low, and so is wind power.
Okay,
So,
because I was interested, they had it last year. They had that TV show called Snake Oil. Did you see that?
I do remember that, yeah.
And I was so with David Spade, and I said it. I saw in the paper about snake oil, and
Yeah.
I thought, well, that is that, but I thought that was rather-
Admittedly, that was to generate some interest. So,
yeah. So I think solar energy, yeah, probably good because we used to live in Arizona where they had this solar.
right.
It was good down there, but here.
So, yeah, it is big. It's also big here. There are a lot of solar
They do have-
installers. There is one in town, Soul Coast. I think they're still in business. And they do solar installations, also passive solar. So years ago, for those that remember the oil embargoes of the 1970s, we got really interested in alternate energy at that time. And at that time, photovoltaics were not a big deal. We cared more about thermal solar. So that became the government was putting subsidies on equipment. And in a lot of cases for adoption, the government has to throw some money into it to make it attractive. So I don't know what kind of monies they might be offering right now for a solar installation. I do know the prices have come down. So if you wanted to put one on your house, I wouldn't say you're making a foolish move, but just be eyes wide open. The one thing you need to know or to ask good questions about is, how much is this going to cost? How much can I sell my power for? And when is it going to pay for itself? So I have a friend of mine who's also an engineer up in Portland. He was looking at one. And one of the things he ran into when he was getting a quote to put a system on his house was his insurance company would not insure it unless he put a new roof on the house. So you have to be careful about things like that. The things that aren't direct cost, but indirect cost. So it costs a lot to put a roof on a house. So maybe that's something you don't want to do right now. Now, in terms of doing this yourself, this is really not a DIY kind of exercise. In fact, electricians have to have special certifications to do solar installations. It's now in the National Electric Code, and you can read it and see what's involved. But in general, it's really not something an individual would take on for themselves.
Thank you.
Mhm. Very good. Any other questions?
Any more questions in here? Okay,
Nope.
I did want to mention that these are recorded online. If so, for some reason you don't have a chance to make it here, or if you want to go back and watch any of the other ones, they are posted on our SWOCC YouTube channel. And then our guest tonight also had mentioned that we should have some more of these lectures on this particular subject in the near future. So please be watching for that. I want to make sure I have the right date. Is it February 10th when on the 11th? That's right. Okay. February 11th. It's another Tuesday at 6 p.m. That will be our geology lecture. So please come to attend that if you would. We have, I believe, yes, we have Pat O'Grady. That's actually going to be here, and he is an archaeologist with the Bureau of Land Management. And he's going to be talking about Oregon's rim rock shelter. So if you guys are interested in geology, archaeology, please come out for that. And then just a month after that, we're going to have our biology lecture. And we are going to have a speaker. I remember his first name's Kyle, but I just totally spaced on the last name, but he's going to be going to be here talking about sea otters in Oregon. So if that interests you, please come back out. With that said, I am going to end now, but you're welcome to hang out here, ask questions with our guest, or roam around in Umpqua Hall to kind of check out the building. And again, thank you for being here.
Very good. Thank you all for coming tonight. All right. I'll let you drive.
Had one of those days.